Calvin. I'll find the slideshow book. Let me get my notes. You'll have to excuse me if I check my notes. There is so much nuance and detail here, and I want to make sure I give you guys the best explanation I can. I've spent many years of my life now obsessing with this kind of data and work. So if at any time I say something and you go, I have no idea what he's talking about, I'm going to open this as an open forum, raise your hand, ask the question, I'll repeat it and answer it. Because to me, all of this is the language I spoke with my colleagues for years, and I hope I brought that to you guys so that you can enjoy it just as much as I do. So here we go. I'm Jack Reynolds. I'll be talking about artificial intelligence and solar astronomy. I started my journey in data science in 2018 doing prototype design statistical analysis for a company called Reynolds, which worked with novel methods in monitoring and changing thermostats for industrial buildings. So how can we use data and science to save the most money possible in scenarios, especially where we just don't have people in the buildings. From there, I went to Purdue University, where I worked with two groups. One was Team Supernova, which I'll introduce you guys in a second, working with Core Collab Supernova and Time Series. And the other one was a CMS group, which is a high energy physics group. So if you guys know the Large Hadron Collider at CERN, I worked with data from that machine, which is absolutely phenomenal. And now I work for Securitas Technology as a machine learning engineer. My emphasis revolves a lot around working with marketing data, not because I think that's our #1 angle, but because that's what's most successful in the business. And we're slowly working our way towards behavioral analytics to provide the best possible experience for our clients. How do we use data to figure out what our clients need before they need it? And how do we then take that to action for the business? So enough about my background. Let's jump into physics. So this is Team Supernova, led by Professor Danny Milisalvich. He is not only a phenomenal observational astrophysicist, but an excellent mentor and a good friend. A year ago, I would have given you a longer intro to him. If you are really interested in this work afterwards, I highly recommend you go watch the 60 Minutes he did on James Webb Space Telescope. Diving straight into James Webb, on the left, we've got, I think it's your right, my left, the screens are switched on both sides. That is a picture from James Webb of supernova remnant Cassiopeia A, which is one of the supernova remnants inside of our galaxy. We waited so long to get this photo. His name is on the grant. It was so exciting to get. The false color you see there, so this is not actually the color of the supernova remnant, tells a really unique story about the elements and composition and the way that this star exploded. So we studied core collapse supernova, which are supermassive stars that explode at the end of their life. It would be amiss of me as a scientist to not explain to you why that's important. So jumping into that, we're going to explain briefly a concept called metallicity. So in astronomy, we defy common logic and we call everything after hydrogen and sometimes helium a metal, which is a funny definition. But if you look specifically to the yellow squares here on the periodic table, you'll see that those elements come from exploding massive stars, and some of them come almost entirely from exploding massive stars. So that means just about every atom of oxygen in this room came out of a core collapse supernova. If that doesn't state some level of importance on the work, the pretty pictures definitely did it. So in the physical sciences, it's always a challenge to propose why is this work really important, especially when we get into really fundamental research. Astronomy gets the benefit of having the most beautiful views in the universe. So that's a little on core collapse supernova. What I did with them was not just observational astrophysics, it was machine learning. So my job for just about 3 years with this group was working on a program called Refit. So a little bit of background on what Refit does so you understand why we did what we did. There's a telescope going live in Chile pretty soon called Vera Rubin LSST. It is going to scan the entire night sky in multiple colors at a depth we, 20 years ago, could have never imagined, seeing objects dimmer than ever before. And it's going to do it constantly. So we can detect things like exploding stars, which we only can see for 60 or so days on a regular basis. This poses an issue because in astronomy, we got to pick which stars we studied before when they exploded. Now there are going to be so many of them, we can't possibly go through them all. And by the time we do, the data is gone. So that's where I came in. So Refit we started development of it in 2019 and continued to develop it up through publication, which I believe was 2021 or 2022. We're working on version 2 right now. But there's a lot of cool techniques I want to analyze in here. So what refit does is it takes in time series data, so this is sparsely sampled, error-filled data, and then projects it outwards, and then uses those projections across all the possible candidates to select the ones of the most scientific value. So machine learning plays two valuable roles there. One, it gives us those projections. Two, it quantifies most scientific value, because we do not know the fundamental mechanisms behind a lot of these explosions. And for some of them, we don't get enough data to even figure out what caused them in the first place. So for a machine learning algorithm then to say, hey, I have these 30 telescopes in these places on Earth, what's the best course of action to collect data is an immensely valuable proposition. I don't know if the website's technically live right yet or not, or we still haven't closed demo, but if you search refit and there's a website with a very nice interface that people work very hard on, that is what that is. But I know some of you are interested in the details. So when we started this, time series analytics and machine learning was still very much an immature field. I still consider it to a large extent a very immature field, especially when it comes to sparse and error-prone data. There just isn't one algorithm that really screams, I perform on this type of data. So what we did was we actually took image classification networks. So specifically, we used a variation of ResNet 50. We cut the classification layer off the end, added our own dense network, and then used that as an encoding to run k-nearest neighbors to compare similar candidates from both computer simulated data using our current theories and actual observation data. And the reason why integrating actual observation data made us pretty much best in the field for this was because there's a telescope in California called ZTF that's just a mini Vera Rubin LSST. So LSST observes in 6 different colors multiple times a night. ZTF only does 2. So if this graph were to, the graph on the left would be ZTF, it would only have 2 of the rows, specifically the G and R columns. So that's a little bit about that algorithm. If you have any questions about that technique, I highly encourage you to ask them. But know that there are better time series methods now. Anything you do, you look back 3 years and say, yeah, I would have done that totally differently. But at the time, that's what we did. It was super exciting. It was a great project to work on. So I know you're all looking forward to the upcoming solar eclipse. I've already told you that our star, the sun, will not explode. The solar eclipse will not explode the sun. That's a question I've gotten. But what is a solar eclipse? There's this funny picture, I couldn't find it, where it's a quiz. You're asking elementary level students, hey, these different astronomical events. They go, well, it's lunar eclipse. Well, a lunar eclipse is when the sun, or the Earth passes between the moon and the sun. Oh, cool, what's a solar eclipse? And the logic naturally follows then that the sun would pass between the moon and the Earth. That is not what a solar eclipse is. But there is some nuance to solar eclipse. Why do these things not happen all the time? What makes the total solar eclipse so special? So most of the eclipses that you'll see come up on the news or that you'll be able to witness in your lifetime are annular eclipses. So that is when the tilt of the moon aligns with the sun such that you can see the eclipse. Obviously, that's a precursor. But the moon's also what we're going to call past the focal point of the Earth-Sun combination. So what that looks like on the display is that if you draw lines from the outside of the sun over the edges of the moon, they will cross before they hit the Earth. What that means is that light from either side of the moon reaches every observer on the Earth. So it doesn't get totally dark. What's really special about total solar eclipses and why they occur so infrequently is the moon actually has to be closer, which it often is not, such that those lines do not cross at the very beginning. That's also why when you look at solar eclipse maps, that path of totality has a wider band. Anywhere in that band, the moon is going to be entirely encapsulated by the sun. So if you didn't want to drive closer to the path of totality or didn't have somewhere to go in there, as long as you're in the range, you're still going to have a phenomenal experience. So that's a little.
I'm going to ask a question just because I got confused a little bit. So this is a picture of how it happens when it's a total eclipse.
Yep.
But when it's, can you flip back a slide to that annular one? I just wanted to see where the lines, how are the lines different that you were talking about?
So the
there.
lines
Okay.
from the edges cross before they reach you, meaning that the light from each side reaches you still. So the level of darkness isn't the same.
So in the annular, it's that you see the moon and you see parts of the sun on each side.
Yes.
Versus the total eclipse, you don't see any sun, not even a ring around the moon.
Yes, you're gonna, you're gonna see sort of the ring of fire, as it were, which is a really unique experience. We will talk about exactly how to observe the eclipse safely at the end. I know that's important information because everyone's living really close to the path of totality. Please do not look at the sun. I will say that multiple times. You would be surprised how concerning that becomes. But let's talk about solar observation a little bit so I can walk you into the machine learning projects we're going to talk about in solar astronomy. The way that we observe the sun, there are space telescopes for it, but there are also Earth-based telescopes. And a lot of times Earth-based telescopes have the benefit of being able to be really big because it's really expensive and really hard to put a really big mirror in space. That's why James Webb was way, way past its deadline when we finally launched it. So we observe the sun with Earth-based telescopes. The one you see on the top is, I wrote the names down because I always forget them. Pierce our solar telescope, which was built in 1962. It was the largest solar telescope in the world until it was superseded by Daniel Space Telescope on the bottom in 2019. So big gap in solar telescope funding right there, NSF side. Why is it important that we observe the sun from both the ground and space? Well, if you look at the plot I've got there, we all know that UV light causes sunburn, it's dangerous, that's why we wear sunscreen. The sun puts out a lot of UV light. The actual amount of it that hits you is much lower due to the atmosphere. So the red curve there is the actual light coming from the sun that makes it to the ground. The yellow curve is the actual emission that we observe from the sun. And then finally, the black curve is the ideal black body radiation for the surface temperature of the sun. Basically, if you have any object at a temperature which is either large enough or homogeneous enough, you can idealize the model as a black body. You see it actually fits fairly well. That modeling is the same way we figure out the temperature of other stars throughout the universe, because obviously we can't go send something to them and measure it. It's actually fairly hard to measure our own star. A couple of the notes there, because I'm going to be using spectra in a lot of these explanations. When you look at this, you'll see that the wavelength is measured on the bottom and the irradiance, or what I'll refer to as magnitude or flux, is across the y-axis. Those are super, super specific colors. So you think of camera, you think red, green, blue. This is like this one specific 1 nanometer wide shade of blue, red, etc., or all the way into the infrared and UV light. So that's a little about solar astronomy. As we go into it, feel free to ask any more questions you need to understand the data, because understanding the data is how you understand the nature of why these algorithms are built the way they are. And our last piece before we get into the modeling is understanding the phenomena we're trying to measure. So I'm going to talk about 2 different phenomena that we've built models for, not we, but the scientific community as a whole. That is monitoring sunspots and solar flares. So sunspots have a really cool and storied history. You'll notice the sunspot data here goes all the way back to 1600. That's a long time to have scientific empirical data from. There's not a lot of fields that have that kind of reach. And you'll notice that as it goes forward, we get a little more precise. But that's actually because Chinese and European astronomers were keeping track of sunspots all the way back then. Those are just little black dots on the sun. They're like, well, these are weird, what happened? Can you imagine that you started observing these around 1600? You're like, wow, I found hundreds of these. And then a mere 50 years later, like, I can find like 5 of these, what happened? But they kept observing them, and we actually call that the Maunder minimum. That's after one of the scientists who observed them. It correlates with what's called the mini ice age environmentally. Now, the mini ice age is actually from volcanic activity. The sun dimming just a little bit didn't actually cool the earth all that much, but it's interesting that they correlate. And that sort of spoils why sunspots are important, because later on we started experiments to notice that we can tie the number of sunspots to a lot of phenomena that are actually in the sun. The second thing might scare you a little bit more, and those are solar flares. So the scale at the top is how we classify solar flares. A B is 10 times smaller than a C, is 10 times smaller than an M, is 10 times smaller than an X. To put in perspective, if an X-class solar flare hits the right places on Earth, we're looking at like countrywide blackouts. So if you guys were aware of the AT&T outage that happened just recently, there was some M-class solar flares that correspond with that outage. People were like, was it the solar flares? It was not the solar flares. But this may seem kind of like alarmist behavior, right? These scientists, we want to study solar flares. Maybe we're just making these seem more dangerous than maybe they really are. And I've gotten that argument before. We've only really been able to study solar flares for about the past 20, 30 years effectively. We've really only had this technologically dominated society for what, 40, 50 years if we're generous, where it's really hypercritical that all this infrastructure works. So one of these really could hit, and it really could be a problem. And how we anticipate and react to that is an important part of not just our national strategy, but probably our strategy as a species at this point. So jumping into predicting the solar cycle. Oh, do I have a question?
Yeah, I wanted to peek it just while it was on the topic.
Oh, absolutely.
Just because you were doing the general pop consumer science bit about solar flares, which is like, just to give context, that like M scale and even X scale thing, for the alarmists or for the more pessimists or concerned people in the room, what's the time duration on something like that too? Like, oh, this hits and this impacts some things.
Yeah.
How long is that flare? Are we talking like with a couple minutes, weeks? The high intensity, like the main.
Yeah, the high intensity should be pretty short. The exact duration isn't perfectly my wheelhouse, but I can't imagine that the actual flare hammering the Earth, so that the way that we measure flares is with X-ray radiation. The actual X-ray burst would be all that extended. Maybe a day or two tops would be my guess. The impact of that though
Right.
is
Engineering
destroying the
and all that,
electronics. So the societal impact is much longer. But yeah, the actual
But thanks for that
physical
perspective.
impact. Yeah. Oh, and when you look at the solar
Leave
flares,
Michael's in mute.
the other neat thing about them is you often see them associated with coronal mass ejections. So that's this big shiny part here. When those hit the Earth, they cause the aurora borealis, which is very, very cool. The actual solar flare in this picture is over here. So coronal mass ejections are often associated with solar flares, but they're not exclusive to them. If you are doing your own research, that's one of those things that kind of shouldn't be that deep in the literature, but is for some reason. So jumping into our sunspot predictions. Why do we want to predict sunspots? Why do we care about the little black dots?
Hold on, Jack.
Sorry
can I
to
throw it?
interrupt. Yeah,
Oh,
we actually have a few questions from online too.
Oh, absolutely.
So what causes the peaks at certain frequencies, and how did they do that at 1650?
That is the next slide we're going to talk about.
Okay.
That. So look forward to that. That is the whole next project. That's a perfect question though. Did we have any other?
That's it for now.
Awesome. So jumping into predicting the solar cycle, you noticed the frequency. Isn't that weird? What is making the sun dim and brighten on an 11-year cycle? That's just sort of weird. What's the point? Why is it there? So you'll notice that the data we have on solar cycle variations only date back to 1975, even though we've been monitoring sunspots for much longer. So to trace our historical data back, we have to correlate sunspots and solar irradiance, which this plot does beautifully. The yellow is the daily, just to show you how much variation there still is within a day. But the red is the annual, and it really does go up and down on an 11-year period. The other thing that happens, and we didn't know this, we didn't know any of this till we started deploying space telescopes that could measure the sun like this, is that the sun's poles, its magnetic poles actually switch every 11 years. So if the magnetic pole switched on Earth, that would be quite the problem, because your compass would then point south. The sun does that every 11 years. I am not enough of a solar astronomer. My focus was in core collapse supernova to give you all the details of the mechanisms behind that. But it's quite cool that it happens over 11 years. We're not entirely sure why specifically it's that way, and how we figure that out actually has great implications in how we measure other stars and how we understand things like pulsars. But predicting the solar cycle is quite a challenge. I said it was 11 years. 11 years is kind of a rough estimate. We've got a long time to say it's 11 years, but it's kind of rough. Why does it matter? Well, you'll notice that if we plot the solar flare index, which is the green line, over the rest of the data, they kind of line up really well until the last cycle in early 2000. So as our solar cycle has begun to accelerate, get stronger, we're also seeing more solar flares. Obviously, we don't have that much data. We only really have about 3 periods of data here. But understanding that, especially in the technologically dependent world we live in, is really important. So a lot of people have actually worked on this. The plot to your left, my right, is a plot of all of the machine learning experiments that have actually been done to try to predict the solar cycle. And there's some really, really cool stories here. So we've got sort of three stories. We've got our generalized machine learning methods. Think of anything you can pull out of scikit-learn. Literally, that's where they're getting these. Astronomers had been using Python for quite some time to process all of their data. So we were very agile in being able to deploy these type of machine learning methods, especially when they're as accessible as something like scikit-learn, sklearn, yeah, scikit-learn. Even further into Keras, which is for deep learning, very accessible, and then eventually into PyTorch, which we'll talk about a little later. We've got our first three samples, which correlate with 1, 2, and 3, which you'll notice kind of sit off on their own little islands in the top corner. Those are all basic LSTM models. Call it stacked, call it single layer. They're using LSTMs with multi-layered solar data, so multiple data points at any one time, to try to predict the next solar cycle. This comes with its pros and cons. The major con being that you really don't have an error bar associated with the data. You can do some ensemble modeling to get an error in time or an error in magnitude, but you really can't get both. And it's just, you don't have the confidence there. You'll also notice that all of those are kind of off to their side in their own space. Where we really see a cool jump here is with the Bayesian LSTM. That one not only took into account the error in the data innately, but also took into account its own ability to generate an error, not using ensemble modeling, using Bayesian techniques. So you'll see that one will actually land about in the middle of where we're seeing the rest of our models land, which is typically a good indicator in physics. You've got multiple models saying the same thing, you've probably found the right answer. In machine learning, that's a little more, maybe they're all picking up on the same feature, but to physicists, this looks great. So we've talked about the basic scikit-learn models. We've talked about sort of that LSTM evolution, where we're not only just maturing as a field and using deep learning, but also evolving it to fit our data better. The last one I want to mention is really special to me because they use a very similar technique to what we did with refit. So in refit, we took a ResNet 50 image classifier, find the cat or dog, and we cut the bottom off of it and used it as a k-nearest neighbor encoder for supernova explosions. This was a crazy idea. We had so many people tell us this was a bad idea, and it totally worked. This group used WaveNet. You're like, what's WaveNet? So WaveNet is effectively an encoder for audio data. So you've got your literal audio wave profile, you run that through the WaveNet encoder, and you get an encoding space. Now, obviously, you could use that for classification or transcription or something of that nature. Spectrographic data is a wave. It's measured in nanometers. Radio and sound just happen to be measured in hertz, but it's at the end of the day, it's the same unit. So it's sort of an intuitive use, just sort of out of the box for the use case. So they took WaveNet, they cut the bottom off, and they used that as an encoding for an LSTM input. And then they pushed that through. And I actually think of all the results here, I like theirs the most. It's got sort of the wider error of all of them. It's number 7 there. But I think that their methodology utilizes machine learning and artificial intelligence as a field well to support their work. They have this enormous depth of knowledge in solar astronomy, the features, what we're looking for, what's important. What a lot of us don't have is that depth of knowledge and how to build deep learning algorithms and how to use it when we don't have nearly enough data to do so. I showed you we only have a little bit of solar data compared to the timescales we're working at. When I worked with transients, it's sparse, it's not complete, most of the samples aren't any good. So to be able to leverage another part of the field that has something that's much more common, like audio data or image encodings, it's a really powerful tool. So if you take one machine learning technique away from this meeting, that is what I would say. Find something that does almost what you want. Don't be afraid to take it completely apart and then utilize the weights from that algorithm, because you will find that even if it doesn't seem related and it seems really weird, there's a remarkable amount of novelty in there. Does anyone have any questions on these models in here?
Sound like there is.
Oh, brilliant.
Do you want me to read them, Calvin? There's a few from online.
Yeah.
So Dave Campbell is asking, he sees WaveNet that he's familiar with. And there's another one from Timothy. What are your thoughts on auto ML frameworks like AutoGluon?
So I can't speak specifically to the framework because I haven't utilized that one. Generally speaking, AutoML is a great solution in sort of like a fast, high production environment. But I think that it fails to capitalize on the nature of data. If your data is time series, if it's sparse, if it's categorical, AutoML is still going to test solutions, models that aren't necessarily aligned with that kind of data nature. Now, if there's an AutoML structure out there where you can tune out models you don't think are relevant, you'll have to just discard the comment. But generally, that's my view on AutoML. You don't see it used a ton in physics, which I found interesting because it definitely lowers the barrier to entry. But it's never really become popular in the field, at least in the parts of it I've interacted with.
It's very interesting. I'm kind of curious, because these are only about 2 or 3 cycles that you
Yeah.
observe. I would be worried that this is somewhat overfit. I mean, as a base case or a null hypothesis. But what about a simple FFT?
We can go even simpler and just use linear regression. So there is a linear regression model mixed in there. It's number 8. So yeah.
But I would be curious at that first end.
You're
what's the spectrum?
absolutely right.
And see whether that should sufficiently predict at least the.
Yeah, no, I absolutely agree with you. That is the challenge of this work, is there just isn't that much data.
It smells overfit.
Oh, a lot of things fell over fit in the field, absolutely. That's why I love the WaveNet solution. Because of them, I think it's the least likely to be overfit because the encodings are already built.
But see, WaveNet is in some sense, because it's used for speech synthesis, it's literally, you could think of like a selector of different wave. So
Yep.
again, that's what alarms me, that it seems like this is basically overfit.
Yes. No, I believe especially the top LSTM models are most likely overfit. But that comes down to how robust and how much you trust the groups. When you read a machine learning paper, there's a lot of details about their training procedure and how that works. When you read a physics paper, sometimes they just go, it works. And that's good enough for some reviewers and that's not good enough for others.
But this probably certainly publishes easier than loading it into Audacity and doing a spectral analysis.
Yes. Tough. Did we have any more questions from the online group?
Are there any more online questions, Laura? I think we're good.
Not right now. We're good.
Perfect. So we'll move on to our second piece, and I'm going to drop another interesting technique here because that's what I enjoy, which is explainable ML. That's the idea that we build an ML algorithm to answer a question, but we also want to explain why that happened. That's really, really important in the physical sciences. So I told you about my work with Supernova, and I said we don't really know how some of these things work. At their intricacies, what makes these things special? What feature in this makes this different than this? And we can't always answer that question. Explainable ML takes a big step towards interpreting data. This paper is going to use something called GradCam, which is available on GitHub. I wrote down the name of exactly what that stood for, but generally speaking, it uses the gradients to place feature importance backpropagate feature importance. If you want to utilize this, I know I'm not giving you nearly enough details to go and just use it. It is based on PyTorch frameworks. So temper your expectations if you're like me and love Keras too much. So they're using explainable ML in this case to do 2 things. One is what the authors of GradCam actually intended. They're going to use it to differentiate between multiple models that have fit and choose the one that fit to the features that actually make sense in the science. So you think of that in terms of an image classifier, you've got something that's classifying different types of wall materials. Well, you see that it's highlighted the grout lines in the brick. You're like, oh, that's great. Well, the other one just picked up that it was red. You may not have enough data for those models to look different in their actual performance functions. But if you look at the GradCam gradients, you can see that it's picked up on important features. So it's a way for someone without a depth of knowledge again in training to look at the results of a model and say, this is a better model. In this case, they want to see how detailed of an explanation can they get, because they may learn something. And they'll be able to pick the best model, because when you're predicting solar flares, it's not just for discovery. There is a very real use case. Can we predict these early? Can we prepare for them ahead of time? So what you've got on the screen across the top are actually the spectra. I showed you the friendly spectra before. This is what they look like when they come out of the telescope. The one on your guys' right, the one that looks nice and thin and clean, is a really nice spectra. The other one is not nearly as nice. And that's one of the challenges with this, and one of the places machine learning shines, because it can interpret data that can be very messy. And you'll see a use of GradCam to actually filter through that. So the objective of this piece is to take the data from a solar flare potential location and effectively classify, is there going to be a solar flare here or not? And you can see at the bottom, we've got our two solar flares. You've got one on the top, which jumped up. You've got a solar flare, and then you've got the actual region of the data that we're going to feed the machine. And then on the bottom, you've got another one that is not a solar flare. You can see in the image, the way that they've pulled the contrast out in the image definitely highlights the one with the solar flare, and you're like, I don't know, that looks really bright. It's because it is. So it's sort of, the picture's sort of deceptive there. So when we get into actually training the network, and this is just a feed-forward convolutional neural network, and applying GradCam to it, we process the data into this, I think it's beautiful, interpretation of the spectra. So you can see that on the cleaner spectra, it obviously highlighted the regions where it actually picked up data as more important than the regions it didn't. That's an awesome start. But it specifically picked out certain regions in the spectra wavelength-wise. So you'll notice we've got two really strong bands. Sorry, to explain this graph a little better. The y-axis is the wavelength. Think of that as the color of light. So those two strong bands are basically one color. But it also picked up on that much lighter band you might not have even noticed between the two. In the GradCam interpretation, that band lights up really bright. And that is at 2798. That is a magnesium-2 emission, which is the second ionized state of magnesium on the surface of the sun. That is a really important indicator of an imminent solar flare. This algorithm took the raw data, correctly interpreted it, and then eventually, I'll spoil it, it predicts there's going to be a solar flare there. The bottom one's a more difficult story. If I handed that spectra to an astronomer, they would tell me to go retake it. It's messy, it's hard to look at, but we still do have our definitive two lines there. So it's a solar spectra. Those are, I don't know which emission lines those are, but they're very bright, so usually something very important to solar spectra. But you can notice that GradCam still picked up on those intermediate lines the best it could. It's broadened, it's important, its feature importance, but it's still focusing on finding the right features to predict a solar flare. And that's the piece, that's it right there, is not only did we build a machine learning algorithm to predict solar flares, albeit like 4 minutes ahead of time, but 4 minutes is 4 minutes. So if that's how long it takes to shut down critical things like hospital infrastructure, government infrastructure, before we know something like a Class X flare could hit, that could be something that really does save lives. So a few minutes of prediction early, but I would be amiss as an astronomer not to, one, show you the pretty pictures, two, tell you a little bit how the data is actually collected. So we can't just take a picture of the sun and generate what's the flare probability across the whole thing. We don't get detailed enough data to do that. There are definitely works that have tried with some level of success. We have to take spectra. So the spectra taken of these solar photos are actually imaging, like you see on your right, between the two green lines, or in the case of where the green line is really thin, just on that green line. They got one more important result from this, from GradCam, from interpretable machine learning, that you get a higher level of feature importance if the region it thinks is going to have a solar flare is better centered in the spectra. That intuitively, you looked closer at the object you wanted to observe, just makes sense. But for it to show up not just as, hey, these are the important features we want to find, but this is how important the features are, shows that level of depth this analysis actually managed to reach. So I think that's phenomenal. I hope you guys think that's cool as well. But if you take away anything, know that if you've got deep learning running on PyTorch, GradCam could be a great option for you to begin to understand why your algorithms make the choices they are. And that can help you do things like eliminate biases or pick a better algorithm. I had a picture for this and I don't have it, but think of the latent training space in 2 parameters and have a circle in the middle that indicates the right model, the perfectly fit model that's going to solve all your problems. When you train it, you inevitably will never know if you're in the dead center of that zone, or even if you're in it at all, because you don't have that level of insight into how these things perform. When they trained the models for this project, they had multiple models that reached that final fitness point. But by using GradCam, they actually managed to identify which model was picking up on features better than others. And that's one of the ways they deal with the fact that there again isn't great high quality data on all of this. The sun, we have a great advantage for, is really, really bright compared to the rest of the universe for us. That means we can collect a lot of light from it. But when you start to zoom in on features that are only about 10 kilometers wide, that can become quite the challenge because high resolution data to field predictions doesn't exist in large quantities. So I love the use of GradCam in this, if you can't tell. So that's solar astronomy. That's some machine learning projects in it. There's a lot more. The literature review that I based a lot of this work off of is 96 pages long. So if anyone would like to read that, I actually do recommend it. I think it's fairly well written. If you have a basis into machine learning, you can skip like the first 45 pages because they just talk about all the models. But I know a lot of you are really excited for the solar eclipse coming up. Talked about what the solar eclipse is, why it's so special. Now let's talk about why you really should show up to this one. So this one is the giant orange one. Thank you, NASA, for highlighting it. On April 8th, 2024. It's passing right through central Indiana. That's super, super exciting. The next time you will really get a chance to see one of these in an accessible fashion, I believe is 2045, which is going to be the one that runs from Northern California down to Florida. That's the next good shot you'll have at a total solar eclipse. There's also one in 2044 that passes through Montana, but it's kind of a hard window to hit because it's rather narrow. So for most of us, this is really a once in a lifetime experience. I was talking to the professor that trained me, Daniel Salvage, and I said, hey, is this really a thing I should show up for? I am a deep sky astronomer. The sun is the annoying thing that makes it so I can't do my hobby during the day and I have to be up all night. And he said he almost, when he got his job at first, took a big trip to go see one of these. And he waited and he waited and he said, this is one of those once in a lifetime moments where you really get to look around and say, this is my place in the universe. And I'm watching it at work. These forces so much larger than I could ever imagine. It's a once in a lifetime experience. It's breathtaking. I'm already excited and I haven't even seen it yet. So let's talk about how to do it safely. I'm gonna lay down a couple of rules. Do not stand in the street and look at the sun. Check out what's going on around you. You are just gonna wanna stare at it. You're not gonna wanna worry about the rest of the world. So not to quote the CPR class, but is the scene safe? When I watched the eclipse, 2016, we had a partial solar eclipse run through central northern Indiana. I did watch somebody just walk into the street. And I was like, what are you doing? Please don't do that. The other thing is, buy a good pair of solar glasses. You can use them for more than just the solar eclipse. We talked about sunspots. If you have a passing interest in sunspots, you can in fact see sunspots with solar glasses. I don't recommend staring at the sun for extended periods of time still, but there are other things you can do with them than just look at the sun just this once. But even if you look at the sun just this once, a rated, reliable manufacturer of solar glasses will sell these for like $3 a piece. So get some nice ones, enjoy the experience. If you're looking at solar glasses, I put Celestrons up there. You can buy those from High Point Scientific. If you have a whole crowd of people that want to, you can buy a pack of 1,000 of them from High Point Scientific, or you can just buy one. When you buy solar glasses, regardless of the supplier, regardless of the brand, they probably, and I don't know any exceptions to this, but I'm not saying they don't exist, are silvered like a mirror on the outside, and you should be able to see your reflection in them because they should be blocking being reflecting 99.9% of the light. If they just look like tinted sunglasses, they are not solar glasses. Unless there are, again, exceptions to this rule, but if there were exceptions, I feel like I would have seen it in photographic equipment, and the solar photographic equipment also looks like that. So if you would want to play it safe, that is the rule of thumb. You shouldn't just be able to look through them like tinted glasses. And yeah, that's the solar eclipse. One last thing to know, a lot of you will get solar glasses and look at the eclipse. Depending on where you're at, you may have up to 3 minutes of eclipse time. Take a moment, sometime in the middle, to look around at the world around you. Without the solar glasses on, it'd be very dark if they are on. One, you're gonna see a bunch of people gaping in awe at one of the most magnificent events we can witness from space to Earth with our own eyes. Second is the world will be dark and the animals will be doing funny things. Nature was not built for the sun to go out during the day. It's not a common occurrence, so the animals will act up. There are lots of historical references of how events in history have changed because of solar eclipses. If you're interested in that kind of thing, I would highly encourage you to research them. The things like, we were gonna go to war, but then the sun went out, so we've stopped going to war. I oversimplify that, surely, but take a moment to look at the world around you. This is one of those events that are just majestic. People pay a lot of money to travel out to see these too. They do solar eclipse tours, you pay like $20,000, they'll fly you out to one. But I think total solar eclipses only happen earthly about once every 2 years. In terms of annular solar eclipses, you probably get about 2 a year. So enjoy it. This is a really awesome experience. We're all very lucky to be right here when it's about to happen. I'm so excited. Does anyone have any safety questions about solar eclipses? Because I feel obligated to answer those.
The glasses are $3, like I should definitely get them, but I got a welding mask. It's like, can I get away with using a welding mask, or would it just, because I mean, of course, I've used it welding before,
Yeah.
it just shuts everything off and all you see is the arc. But is the UV radiation similar enough to like a serious electrical arc that it could work?
So in a strictly technical sense, in my technical opinion, yeah, I think that'll work. I have heard of people doing that before for eclipses. If I were to be liable for your actions, I would say no, just go buy some solar glasses.
Spend the $3.
That was actually my first instinct to go and do that, and looking at the rating you need on welding glasses, they don't even like sell the filter you would need that's safe to look at the sun.
Oh, really? It's not even close.
Okay.
So even like very dark welding glasses are nowhere near the level of filter you need.
What about taking pictures of it?
Oh, yeah, that's a great one. So I am an amateur astrophotographer, so I have a whole very complicated telescope setup. If you are going to use a telescope, like you have a telescope at home to take pictures of the eclipse, I would recommend not doing that. The equipment you need to actually equip a telescope to do this kind of work without it being a hazard to both your eyes or whatever you put behind the lens piece, including but not limited to your house, is expensive. So if you're really into the hobby, if there's another astrophotographer in here, yes, there is an equipment list. It's not cheap, but if you're really into solar, this might be a once in a lifetime for you. If you just want to take pictures with your phone though, your solar glasses should be more than capable. Buy an extra pair, put them over your phone. What I will recommend is that way before the eclipse, you figure out exactly how you're going to do that so that you're not fiddling with it during your 3 minutes of the eclipse. But the solar glasses are roughly the same filter you'd pop on the front of a telescope. From an astrophotographer's perspective, technically anything under 60 millimeters diameter lens-wise, you can get away with just a top filter. Anything past that, you need to start buying other pieces of equipment to filter it away. I still do not recommend sticking solar glasses over a 60 millimeter telescope though. Celestron makes pieces for that. Buy buy the one built for your telescope. You really don't want to play with your eyesight on this one. If you do it with a telescope, you can go instantly blind, so. It's scary, I know, don't look at the sun with a telescope. It's worse than just looking at the sun normally.
And so you had mentioned when you were talking about like the X magnitude solar flare, that in certain cases, it would kind of give us like a 4-minute warning. I mean, what can realistically say like, oh heck, turn everything off? Or like, I mean, what does that actually look like? Is it just like brace for impact in 4 minutes, or can
Yeah,
something
it's-
actually be done?
So there's a couple of things, because obviously there are documents on like, what could we do? One of the big things from our perspective that's super, super important is they could send us all national weather alerts. Like you get an alert for a tornado or anything like that. They can say, hey, there's gonna be a solar flare in 4 minutes. All your stuff's gonna stop working. Freak out as little as possible. So I think there's value to that, to public awareness. But yeah, generally speaking, I think the big things, hospital infrastructure, things like that, given the right procedures, we have a better shot at, okay, the flare's done. We can flip it back on and it all still works. But yeah, 4 minutes is not a lot of warning. It's obviously not as much prep time as I think anyone would want for something like that, but at the end of the day, that's probably what we can get.
I'm gonna add on to that. So the 4 minutes, if you have more data over more time, is it possible that in the future we could create a warning that gives us, 30 minutes?
It's a good question. It's a difficult question. So these phenomena kind of pop out of the sun. So until there is an optical signature of that phenomena, we really don't have a great method, or a radio signature, we really don't have a great methodology to detect it early. So certain wavelengths of the electromagnetic spectrum, certain particles travel faster through space than others because they run into less things. Yes, there are things to run into in space. But generally speaking, optical is where we're gonna go. So there's about 7 minutes from here to the sun, if I remember correct. Is it 7 or is it 14? It might be even more than that, it could be way off. So you've got that kind of delay there before you could have any chance of observing the physical phenomena. And then on top of that, the phenomena forms mostly under the surface of the sun, so there's not actually a signature for it there. If I were to speculate, there might be some work that could be done with neutrinos that could give us a larger window, because neutrinos interact with very little. So when a neutrino comes out of the sun, it basically shoots a straight shot through. Whereas when light comes out of the sun, it does a literal random walk around the sun. It takes especially for light, a very long time for light to come from the center of the sun all the way to the outside. So we're actually seeing light that's a lot older than just the distance to and from. I'm ashamed I don't remember the number off the top of my head, but you can do the math and like average it, and it actually does come out correct. And from that, you can estimate how much energy the sun actually puts out, and then you go check the measurements. You're like, oh, actually, that's pretty close. So the math is, I'm not going to call it easy math. It's still calculus 2, calculus 3 level math, but it's, for being able to model something so massive in nature, remarkably accurate for the level of elegance involved.
This is kind of a fun, this is more the interdisciplinary exploratory question. But given the broader span of like, oh, the preliminary reading and research you had to do, and then the application of this project, you have lots of time to go to sleep, wake up, shower, think about passively in the background. Were there any other things outside of your immediate work where you thought about, well, I would love to see this method applied to this other completely different industry or domain? Or did you have any, why not, or why hasn't this thing that I'm doing right now had this effect somewhere completely else in the economy or world? Did you have any random?
I'm gonna have to sort through that,
Random
because
connections?
that's my brain 24 hours a day.
Any observations or patterns? I know it's a big question, but.
Yeah, I'll try to pick a good one. I tried to hand those little pieces out. I'd say GradCam applications and other methods like the GradCam is far from the only attention feature mechanism that exists. There are plenty of others. That's just the one that was used in solar astronomy. So I just follow up on that. And industries often find a tool like GradCam. So GradCam is used across multiple papers in solar machine learning because they're collaborating. They've shared the tool, they go, oh, that worked for them, we're gonna do it now. Where I sit right now, and a lot of the work I'm working on is time series transients, so obviously I want to apply that backwards. Identifying features in spectra for supernova would be a phenomenal use of that, because that would help us draw definitive lines between classifications. Is it a type 1, a type 2, type 2b, type 2c? Because people debate that all the time. In terms of something that's more generally applicable and less specific, I think that behavioral analysis is another one that I do for work, would be a really valuable application of this, because when you analyze something like client behavior and client success, you don't just want to get, will they succeed? You want to know why they're succeeding or why they're not succeeding. Because that can make a real business impact, where you can go back and say, hey, we have this issue in our billing system. When you click on the site, it doesn't show up. And so everyone's had a bad time. And we can identify this is their pain point. Maybe not the best example with the site not showing up, but you get the gist of it, is being able to not just predict things, but to understand and then make them into action.
So you had the two spectrometer readings. One of them was more narrow, one of them was a lot messier. And you mentioned that the algorithm allowed you to interpret that messier data with some ease. How much usable data does that create for the field that otherwise wouldn't be there, or would have required more effort to get to?
That's awesome, because that is something we actually do, is we use machine learning to classify data such that we can expand our data sets. You've got, 5% of the data that's been classified, it's been classified by hand. Now you have 95% of it classified machine. Maybe it's not quite as accurate, not quite as precise, but it is much more usable. The exact amount that this affects solar is just outside my wheelhouse. The amount that it's affected transient, and especially supernova science, is massive. So one of the pieces that I worked on with a brilliant undergrad, I'm sure going to grad school, Braden Garrettson, he put together the largest list of type 1a supernova samples ever compiled. It was 10,000. We could have gone farther. But that was the level of quality we were comfortable with, and 10,000 is a nice round number. So yeah, we absolutely take that data, classify it. This specific project classifies between is a flare, is not a flare. By nature of how GradCam works, a binary classifier was the approach that showed the best results using that method. But yeah, we do use it to sort the data so that we have data that is usable. A lot of this data is public access. I mentioned Vera Rubin LSST, public access when it starts. I mentioned ZTF, that is public access now. Solar, this is solar, I think satellite, so that might be GOES. There's a lot of them. That is an NSF project, National Science Foundation NASA project. That data is public access after 6 months, depending on the author, it'll be public access after 3. So
Is that data like in a raster format like this, or is it like integers, vectors? What are you seeing?
this is literally a picture. This
Yeah.
is what it comes across from a CCD.
So it's a raster, like bitmap.
It's just, I would call it a vector.
Yeah,
But yeah. It's all it is. They're monochrome in 99% of the scientific data is monochrome. So you're gonna get a CCD sensor sized matrix or vector map.
there's a related question online from Dave Campbell about how many independent channels are available for each image. Assuming a channel like a wavelength.
Yeah, so that depends heavily on the instrument. So you can see why machine learning being able to go through this data becomes really important. So in this case, they've zoomed in specifically on 2804 to 2796 nanometer or angstroms, sorry, which would be 280 to 279 nanometers. Boy, I hope I did that conversion right. I think it's just 10 towards the towards the left. So that's the spectrum that we're seeing in this example. I swear I had another spectrum in this presentation. This one is, I had another one that I'm not showing, which is too bad, which is from 250 to 2500 nanometers. So The resolution depends on the instrument, but it also depends on the placement too, because when you take a spectra, the actual curvature of the mirror can curve the spectra, makes it very difficult to post-process systematically. Another great place for machine learning.
Yeah.
So identify, oh, it's curved, well, I'll just read it on the curve then, whereas an astronomer reading it actually has to go through and plot along the curve and then extract it. So I think I took the pretty spectras out because they just don't tell the story right, but there's plenty of spectras in any of the citations on this, so.
Dave also asked, how many planets will be visible during the total eclipse?
How many planets?
Yeah,
I think, well, it's 3 o'clock. So,
this is in your wheelhouse now.
no, this is still terrestrial.
Yeah.
But I had a friend over the other weekend and I had my telescope out, and when I have people over, I like to show the planets because it's really easy to go find the planet, show the planet. If I want to show deep sky objects, it's set up the telescope, align the telescope,
Yeah.
sit outside in the cold for 45 minutes, wait for the camera to process the photo for half an hour. Oh, look at this fuzzy object I found. And then people are not nearly as amused with that process. So the planets, I think, now they'll just be bright dots in the sky. I think you'll be able to see Mars, Saturn, you might be able to see Uranus. I think Jupiter's below the horizon at that point. Mars might be, but if you are interested in exactly which planets you'll be able to see, about 10 minutes before, there's an app called Stellarium. It's on iOS. I highly recommend that if you're looking for what I would consider to be the premier astronomy app. It is $5. It's $5 well worth it. I use it all the time. I'm biased. But there are also lots of other free ones. You can point your phone at the sky, find those if that's something you're interested in ahead of time.
Awesome. Any other questions in the room for Jack?
What's the plan if it rains?
Cry. I talked about this with the professor. He goes, yeah, actually, I was gonna fly, I think he was gonna fly to Houston. Yeah, he was gonna fly to Houston because statistically, there's only a 40% chance of cloudy skies that day in Houston, and there's a 60% chance in Indiana. I have an app called My Radar where I can actually see the cloud coverage on the radar as an overlay. If it's cloudy where I am, I will try to drive somewhere it's not. Because you can outdrive the clouds. Unless there's a lot of clouds, then you can. But yeah, no, if it's cloudy, it just really sucks.
Awesome.
So.
All right, let's give Jack a big round of applause.
Yeah.
Thanks.